All right, now we want to see, this is the second video about angular momentum. We want to see what is this value, angular momentum, around some point C, which is not necessarily center of mass. All right, so we want to calculate that. We don't need forces now. So this relative velocity of I, point I, with respect to C, this is omega cross Ri. We discussed it in another video, but you should know that the velocity of I is in fact, I mean, because we have Ri with respect to this inertial coordinate system, again, Ri, if I have, call it Ri, and I call this Rc, so I would have Ri equals to Rc plus that Ri, right? This equals this plus this. So if I do the derivative, Vi, absolute velocity of V, equals to absolute velocity of C, plus that relative velocity. And that Ri, the length of that is not changing because this is a rigid body, but we have a change due to the rotation of the system. And that is omega cross Ri. So this relative velocity, or VIC, is omega cross Ri. So let me erase this for now so we don't have a busy figure. So the first part is that we discussed 2D system, which is very simpler compared to the 3D system. So if I have a 2D system, my omega would be in the k hat because everything is planar. So omega is vector that we can use right-hand rule. It shows the rotation. So omega would be some value, k hat, and my Ri would be ai hat plus bj hat, some planar vector, right? So if I do cross product, omega cross that, it would be k hat, omega k hat cross that. You see, let's do that. This is omega k hat cross ai hat plus bj hat. K hat cross I hat is J hat, and K hat cross J hat is negative I hat. So now again, I cross it again with Ri. Then I would have, let's say, AI hat plus BJ hat cross A omega J hat minus B omega I hat. Then I hat cross J hat, it becomes K hat. So I would have A square omega K hat. I hat cross I hat 0. J hat cross J hat 0. J hat cross I hat. It is negative K hat. So I have another negative here. So I would have B square omega K hat. So I can factor out K hat and I would have A square plus B square omega K hat. So you see, and I have that MI. So I have to do summation of MI AI square plus BI square, meaning that I write each RI as AI. You see, I write each II as AI BI. Although previously I used it without I, so you can imagine that. Let's add I here as well. This is for particle I. I just wanted it to not be busy. So they are all for the particle I, right? This Ri is for particle I. So I'm doing this summation, and this is I around that point C. Because it is summation of the distances. This is the this is Ri, the magnitude of that square, right? Because R is AI hat, BJ hat. So magnitude of that is the square root of that. And because this is square root to the power of 2, so this is MIRI square. So this is called I. For 2D, so we saw that for 2D, we would have this, right? Let's just say this. HC. Don't forget that when we do the derivative of that, then we have another term. And if C is not center of mass, we can't write IC alpha. We can't write this generally. So C has to be either center of mass or stationary point, or a point that the acceleration is along the, if there is a center of mass like that, the acceleration of C should be along that RICG. So this is not true for every case, except for 3 cases. But this is what we found for angular momentum. So this is true. And we saw that, okay, angular momentum, we can use that I from the table in the back of the book. Now, what if we have 3D case? All right. So for 2D case, we have just this I is its color. We can find it from back of a lot of books. So what if this is 3D? So we wouldn't have this. It would be IJK and it will be IJK again. So for that, I have to use MATLAB to explain it because I don't want to do cross product 2 times. So I'm doing this cross omega cross R. So I'm doing this first and then this second. So let's do it with MATLAB. So you see, I use symbolic tools in MATLAB, and this is live script in MATLAB. It is not an M code. If you click new live script, this is nice for presentations because you will see the results right here. And it is not, you don't have to run it outside. So, I mean, MATLAB has a couple of different file formats. You see, you can write script, live script, functions, even, for example, a Simulink file. But this is live script. And I use symbolic toolbox. So I define X, Y, Z, and omega X, omega Y, omega Z, and R, my R as X, Y, Z, omega, so omega X, omega Y, omega Z. Then I do this cross, does the cross product in MATLAB, omega and R, so it is omega cross R, in fact. Then this term is, again, I do another cross product, so it is R cross omega cross R. And I do this expansion of that because I don't want it, you will see, let's run it. All right, this is R, this is omega, this is omega cross R, this is R cross omega cross R, and I want to see that like this. So it is omega x y squared minus omega plus omega x, you see, z squared. So let's go back to the whiteboard and let's write them again here. It was omega x, and I just rearranged them. So it is omega x y squared plus z squared. I factored out that thing minus omega y x z x y minus omega z minus omega z x z. And we have some other terms. So we can see that I can write it as IXX, IXY, IXZ, this matrix multiplied by omega x omega y, omega z. You see, this would be Ixx omega x, Ixy omega y, this is omega y, and this is omega z. So what are these Ixx, Ixy, Ixc? So imagine that you have a 3D object. Let's say this is like a cylinder and it has this. Let's say this is, for example, y-axis and this is z-axis. All right, so x-axis is out of plane and it is up. See, I'm using right hand rule, so I have x, y, z. Right, so x is out of plane, y, z. So for a point here, I'm doing this integration, right? I mean, this has to be multiplied by mi as well, the whole thing. So you see, if I have particle mi here, this y square plus z square, it gives me this r square, which is distance from x-axis. This is distance of this point from x-axis. So that's why we call it Ixx. So you see, because we have y square plus z square. So we call this Ixx. Then Ixy, so in fact, Ixx would be m dm r square, and this r is distance from x-axis, right? Ixy, you see, it would be x and y. Then this time I have to draw it x-axis and y. So it is this x and y multiplication of those. So Ixy is not r square. It is, again, I do dm, or I can put it here. So it would be xy, and I need a negative here. So I do this, I calculate this and call this Ixy. And here I would have the same thing, Ixy, Iyy, Iyz. Because if we look at the second line, for the second line, I have minus omega x, and I have yx. Yx or xy is the same, so it is Ixy. So you see this multiplied by this. Remember, the matrix calculation is like that. This times that, this times that, and this times this. This would be the first term, right? The first term. This is this at the end, it will be just a vector. We add these two. Don't forget that this is not a matrix. I mean, this is just a vector. This minus this minus this. This would be the first line. So this, this. So you see, for 3D cases, rather than just having one I, scalar I, multiplied by omega, we would have the I, in fact, in 3D is a matrix. So the angular momentum would be that matrix I. We have other terms here, right? So I would be a matrix in the most general form, which is the 3D. I mean, in our world of mechanical systems. All right, that's it.